This is section 2.6, optimization. Relative extrema. We've actually talked about this earlier. So recall that a relative maximum value for a function corresponded to where a hill occurred in the graph of the function, and that a relative minimum value for a function corresponded to where a valley occurred in the graph of the function. So we're back to looking at hills and valleys. Collectively, remember, the set of all relative maximum and relative minimum values of a function is called the relative extrema of the function. So relative extrema could be a max, could be a min. So extrema is the more general phrase. Notes on the relative extrema. Number one, the x value, which remember that's the independent variable, of relative extremum is where, when, or what makes the relative extremum happen. So it's where it is, when it is, which is when you're using time, or what makes the relative extremum happen, or what causes it to happen. Number two, the y value, which remember that's the functional value of relative extremum, is what the relative extremum is. So the x value is where it is, when it occurs, what makes it happen, what causes it to happen, and the y value, the functional value, is simply what is the relative extremum, what is its value. Now in this section we'll be looking at what are called optimization problems. So we've got to worry about what exactly are these optimization problems. They're not necessarily word problems. So we're going to figure out what does it mean to optimize something. So definition. An optimization problem is a problem in which we try to make something, typically a function, as large or as small as possible. So to optimize a function means get it as big as you can or get it as small as you possibly can. Now that means in an optimization problem we're usually looking for a relative extremum. So be very careful about what you're looking for. Are you looking for the x value or are you looking for the y value? Remember, the x value is where it is, when it happens, what makes it happen, what causes it to happen, and the y value, the functional value, is simply what is the value of the relative extremum. Now sometimes you're asked to find both. Now in order to find a relative extremum using the calculator, we use one of the following two functions that are in the calculator. So we're about to be introduced to two more functions that you may never have used before in your graphing calculator. Number one, for relative maximum value we use the maximum function. It is simply labeled maximum. And number two, for relative minimum value we use the minimum function. Again, it's simply labeled minimum. We just have to figure out where are these things. Both of these functions are located in the calc, which remember calc is second of trace, so they're in the calc menu. Now we've already been using the calc menu to find solutions to equations. We were using either choice 2 for 0 or choice 5 for intersect. So if you press the calc menu again, you get this. So we've already used choice 2, 0, we've chosen choice 5 for intersect. Now we're going to be using choice 3 or 4. So 3 is minimum, 4 is maximum. So remember, you either press 3 or 4, depending upon which one you're doing, or else you can scroll down to whichever one you need and then just press enter. So we're about to see using these two guys. We've already used 2 and 5. Some examples. Number 1, let f of x equal 5x squared minus 8x plus 3. We're going to find in part A where the minimum value of f occurs, if necessary, round to 4 places to the right of the decimal point. Notice it says if necessary, it may not be. And B, we're going to find the minimum value of f. Again, if necessary, round to 4 places to the right of the decimal point. Okay, in terms of x and y, in part A we're looking for x, in part B we're looking for y. Now the calculator will actually do both at the same time. So our solutions. We're going to try to do this step by step. Now remember, we're doing A and B at the same time. The calculator finds x and y at the same time. So step 1, enter f into y1 in the calculator and quit that screen. Okay, so let's get out the calculator. Y equal Okay, and it's 5x squared minus 8x plus 3. Oops, snapped back to where I didn't want it to go. 5x squared minus 8x plus 3, and quit the screen. So we are through step 1. Step 2 says press calc, which remember that second trace, to get the following screen. Okay, let's go ahead and do that. So calc, yes, I have that screen. Okay, so since we're looking for a minimum, right, minimum, we're going to choose choice 3. So now the calculator is going to draw the function. Okay, it's going to draw the function, and then you're going to get that screen. So choice 3. Okay, notice it did draw the function. Now it's asking for left bound and right bound. Notice the minimum is right here. It's also verified that you did key it in correctly. The minimum value is somewhere between x equals 0 and x equal 2. So for my left bound, I'm going to use x equals 0. Since it already says equals 0, I'm just going to press enter. Now you won't be able to see it, but it's going to draw a dotted line on top of the y-axis. You're not going to be able to see it, but that's what's going on. Okay, so you can't tell, but again, there's a dotted line on top of the y-axis. And there's also this little pointer thing. Then the right bound. Okay, the right bound looks like maybe 1 or 2. To be safe, I'm going to pick 2. So again, I'm entering 2 for my right bound and pressing enter. And then it's asking for a guess. And notice it's going to make a guess of 2. Now here you can in fact see that dotted line. So let me get caught up on our calculator here. So the left bound, I'm picking 0. The right bound, I'm picking 2. Okay, 2. Press enter. Now it's asking for a guess. Okay, again, I'm going to go ahead and use the calculator's guess. The calculator's guessing 2, sure, why not? Okay, so my minimum is 0.8000217, and the functional value is -0.2. It turns out this is supposed to be exactly 0.8. There's garbage in the calculator that's giving all these extra unnecessary digits. So the calculator is asking for a guess. Again, I use the calculator's guess, and there. So the minimum occurs at x equal 0.8, and the value is -0.2. Again, these extra digits, that's just garbage in the calculator. There actually is a way to clear out the garbage in your calculator, but it's not really worth doing. It doesn't happen very often, but every once in a while it does happen. So the actual value again is 0.8. Okay, again, the extra digits are just garbage in the calculator. So our solutions: the minimum value occurs at x equal 0.8. Minimum value is -0.2. So again, notice it found the x and the y at the same time. Now it's up to you to be very careful about which one are you looking for, or are you looking for both of them. Okay, example number 2. We're going back to the open top box. So it says an open top box is made from a flat sheet of cardboard that measures 12 inches by 20 inches by cutting out squares that measure x inches by x inches and turning up the edges. So the volume is x times 12 minus 2x times 20 minus 2x. So in part A, we're going to find the value of x that results in a box with a maximum volume, and if necessary, we're going to round to the nearest hundredth of an inch, so that's 2 decimal places. In question B, what is the maximum volume? And if necessary, round your final answer to the nearest tenth of a cubic inch, so that's 1 decimal place. Remember, we did this earlier in a previous section, and I think in that previous section we wanted the volume to be 100 cubic inches or something. So we'll be finding the answers to A and B at the same time. Part A wants the x value, it even says so, and part B wants the y value. So our solutions. Okay, we're going to enter v into y1, so let's take out the calculator again. Okay, quit this. Go to y equal. Get rid of the one that's there. So x, then open parenthesis, 12 minus 2x. Close parenthesis, open another one. 20 minus 2x. Close that parenthesis. And we quit the screen. Now this time we're looking for maximum. So step 2, we're going to press calc. Okay, we're going to get that screen. Of course, we're going to pick maximum. So since we're looking for a maximum value, we press 4, and we get this screen. Okay, now notice so you can actually see what happened. Okay, so second calc, choice 4. Now watch it draw. Okay, notice it's going up, and then it's going to come back down, and then it's going to go back up. The maximum is somewhere up here. It's where we can't see, but it turns out it doesn't really matter. The calculator may still be able to find it. But notice that this top value is somewhere between this x-intercept and this one. So that's 0 and what? 1, 2, 3, 4, 5, 6. So the maximum is somewhere between x equals 0 and x equals 6. So those are my left and right bounds. So again, we cannot see enough to find out where the maximum is on the graph, but I can maybe make the calculator graph it by having a left bound of 0, a right bound of 6, and then whatever the calculator's guess is. So let's go ahead and do that. So left bound of 0, press enter. Come on, enter. Right bound is 6. Press enter. A guess of 6, yeah, sure. Okay, so to 2 places, 2.43. And to the nearest tenth, 262.7. So come on. What's going on here? So again, we saw that. So 2.43 to the nearest hundredth, 262.7 to the nearest tenth. So maximum volume occurs when x is about 2.43 inches, and the maximum volume is about 262.7 cubic inches. Okay, endpoint optimization. So consider that graph y equals x squared. Okay, this is the graph. Okay, now notice there is a minimum value. It occurs at x equals 0, and it turns out the function value is 0. But as I move further away from 0 going left or right, the graph keeps going up and up. So there is no relative maximum. So the graph has a relative minimum, but no relative maximum. Now in order to get a true maximum value for y, we have to restrict our x values to what is known as a closed interval. Okay, all the intervals we've been looking up to at now so far have been what are called open. So we're going to define what exactly is a closed interval. It really just places restrictions on the x. That's really all it does. So definition. Let a and b be real numbers with a less than b. Okay, the closed interval from a to b, and it's noted like this thing, in brackets put a comma b, and it's read, the closed interval from a to b is the set of all numbers between a and b, including a and b. Now these two numbers, a and b, those are called the endpoints. Now the inequality notation for a closed interval is a less than or equal to x, which is less than or equal to b. So x is trapped between a and b, and it includes a and b. So the numbers a and b are called the endpoints of the interval. A closed interval includes its endpoints. Okay, an open interval does not. Now definition. A maximum or a minimum value that occurs at an endpoint of a closed interval is called an endpoint maximum or an endpoint minimum, respectively. So in general, if you have the extremum occurring at an endpoint, it's called an endpoint extremum. Now the process for finding an endpoint extremum is basically the same as finding any extremum, except that at least one of the left or right bounds should be the endpoint of a closed interval. Typically, the left bound is the left endpoint, the right bound is the right endpoint. And depending on whether you're looking for a maximum or minimum, it's going to be either choice 3 or 4. And if the extreme value actually does occur at an endpoint, the calculator will tell you that. If it does not occur at an endpoint, the calculator will also tell you that as well. So to find an endpoint extremum on the closed interval AB, again, we typically let the left bound equal A and the right bound equal B. So some examples. I'm going to pick on that y equals x squared. So it says let f of x equal x squared. Okay, so part A says find where the maximum value of f occurs on the closed interval from 0 to 4. Part B, what is the maximum value of f on the closed interval from 0 to 4? And question C is the value in endpoint extremum. Now we're going to do A and B again at the same time. Remember, A is looking for the x value, B is looking for the y value. So our solutions. Okay, it says f of x equals x squared is already in the y1 calculator. Turns out it isn't. So let's go back to our calculator. Let's quit this screen. Now let's put y1 as x squared. So clear that out. X squared. Squared. And we'll quit the screen. Okay, so now I'm caught up here. So it says we're going to press calc. We're going to set maximum, right, because it's looking for maximum value. The left bound will be 0. The right bound is 4, right? 0 to 4. And again, I'm going to use the calculator's guess. Okay, so if I do all that, okay, if I do all this, so let's see. Second. Come on. Second. Why is this thing jerking again? Second. Calc. Maximum, choice 4. Okay, so there's our parabola. Left bound, it is 0, because I wanted 0 to 4. Right bound is 4. Enter. It's guessing 4, so sure, why not? Okay, so the maximum occurs at x equals 4, and the value is 16. So again, there's our screen. The maximum value occurs at x equals 4 and y is 16. So that's A, that's B. Now for question C, so here are our solutions. Now for question C, though, is the value in endpoint extremum. So it's asking, is x equal 4, is that one of the endpoints of this interval? Yes, it is. It's the right endpoint. So is it an endpoint extremum? Yes. So the maximum value on 0, 4 occurs at x equals 4. The maximum value on 0, 4 is 16. And it is a relative extremum since x equals 4 is an endpoint of the interval from 0 to 4. Okay, number 2. Susie is on her motorcycle in the desert 5 miles from point A that is on a long straight highway that goes through the desert. Point A is 25 miles from a town on the highway. If Susie can travel at a rate of 20 miles per hour in the desert and 50 miles per hour on the highway, how far from point A should Susie get on the highway in order to minimize her total travel time to get to the town? What is the minimum travel time? And round your final answers to 2 places to the right of the decimal point. Again, there are 2 questions being asked here, but of course the calculator will do both. So notice I'm wanting to know in the first question what will minimize it, so I'm looking for x. And the second question is what is the minimum travel time, so I'm looking for y. Okay, we are going to make a little sketch of this problem to help us out. And we also have to remember a little formula that distance equals rate times time. Remember, rate is speed. So our solution. Okay, we make a sketch of the problem. So let's see, according to the problem it says Susie is on her motorcycle in the desert 5 miles from point A. Okay, so here's Susie in the desert. Here is point A. Okay. Remember your high school geometry that the shortest distance between 2 points is a straight line. So, and this is 5 miles. Okay. Now, point A is 25 miles from a town. So, because I've left more room over here, I'm going to put the town somewhere out here. Okay. So, this distance right here, that's 20 miles. Oh, excuse me, 25. 25 miles. Okay, now Susie is supposed to intersect or drive toward the highway somewhere in here between A and the town. And I wanted to know how far from A, right? So yeah, how far from point A. So let's let this be Susie's path to the highway. Okay, so there. Here she is traveling in the desert. Remember, she can only travel 20 miles per hour in the desert. Okay, now remember, I want to know how far from A, so call this distance right here, I don't know, call it X. So X is the distance between point A and where Susie enters the highway. I don't know what it is. Okay, now I got to figure out this distance right here from where she's entering the highway to the town. Remember, this total distance from A to the town was 25 miles. That part was X. So this part here is 25 minus X. So the distance between where she enters the highway and the town is 25 minus X. You should verify that if you add this distance and this distance, you get 25, right? The sum of the parts is the whole. Okay, we got to figure out what this is. If you look at that path through the desert, it's the hypotenuse of a right triangle. So we're going to be using the Pythagorean theorem. So by the Pythagorean theorem, this hypotenuse is going to be square root of x squared plus 5 squared, right? Remember, a squared plus b squared equals c squared. So this side is going to be the square root of x squared plus 5 squared. So square root of x squared plus 25. That's how far she's going to travel in the desert. That's her distance. So square root of x squared plus 25 is the distance. 25 minus x is the distance. Okay? Remember, we're looking for x. So remember, this is coming from Pythagorean theorem. So recall that distance is rate times time, or d is equal to rt. Remember, we're looking for time. We're wanting to, going back to the problem, we're wanting to minimize her travel time. So to solve this for t, just divide both sides by r, right? So I'm going to have d over r is equal to t. Okay? So I've got my distances, and I did have my rates, right? In the desert, she travels 20 miles per hour, and on the highway, she travels 50 miles per hour. So time to reach the town is the time in the desert plus the time on the road. So call it capital T for time. Remember, in the desert, it was the square root of x squared plus 25, Pythagorean theorem, and she could drive 20 miles per hour in the desert. Okay, on the highway, remember, it was 25 minus x, and she travels 50 miles per hour. And here's our restriction on x. It's between 0 and 25. Because again, going back to the figure, if it's 0, that means she drives down this leg of the right triangle. If it's 25, that means she spends her entire time in the desert. Okay? So it's like she went straight to the town without ever getting on the highway. So those are the restrictions on x, between 0 and 25. And notice it is a closed interval. The closed interval happened all by itself. We didn't make it happen. It happened all by itself from the restrictions on where she can enter the highway. So either drive straight to A without going on the highway anyplace else, or stay in the desert to get to the town. So we need to minimize t. So remember, here's our t. We're going to enter into y1, choose minimum, left bound of 0, right bound of 25, and again we're going to use the calculator's guess. So let me key this into the calculator. So I guess I got to turn it back on. Okay, quit this. Y equals, clear that out. Okay, so second square root x squared. Come on, what's going on here? My mouse is jerking badly. X, oh crap. Just start all over again. X squared plus 25. Okay, get out from under the radical. Divided by 20 plus, open parenthesis, 25 minus x close divided by 50. Okay, and we'll quit that. Okay, so second calc, minimum. Okay, left bound is supposed to be 0. Right bound is supposed to be 25. Whoops, I got this error, invalid. Okay, attempt to, now, let me go to this. Remember, 25 is way out here. I should change my windows. Okay, so let me quit this window. For the x-min, let's let it go ahead and be 0. For the x-max, okay, let's go slightly bigger than 25. I don't know, 30. And let's have our scale be 5. Okay, the y-min, it doesn't need to be negative, so let's say 0. And just to have fun with it, let's say 25. And let's have the y-scale be 5. So quit this, second calc, minimum, left bound we're supposed to be 0. Right bound is supposed to be 25. Guess 25, sure, why not? Okay, and there's our answer. I wonder, what did I pick for my window settings here? So we need to minimize t again. We got that. Let's see now, what did I... Now you saw what I chose live. So I'm going to change my window settings. I let x-min to be 0, and oh, I kept x-max at 30. Okay. Left bound is 0, right bound is 25. Okay, notice I did not change my y-min and y-max. Okay, so I think by having 0 for the y-min makes the graph look a lot better. So again, let's compare this with this one. Okay. I'm wondering what's happening though, because I'm getting different answer. If you look at this one very carefully, see if someone can spot the error. Notice that says 2, not 20. This one does have 20. Well, let's go back and fix the function. Okay, notice it's 2, not 20. Again, someone probably saw that while I was keying it in and you didn't tell me. So let's do an insert 0. Okay, we're done with that. Let's trace it out again. So second calc, minimum, come on, minimum. Okay, now this does look a whole lot more like that one. I guess that's why it looks so much nicer. I didn't have the correct function. Yes, that now is correct. Okay, what did I do wrong this time? Oh, left bound is supposed to be 0, isn't it? Right bound is supposed to be 25. Guess 25, yeah, sure. Okay, and the minimum, now they seem to agree. 2.1821792. Okay. At least now you see how to fix some errors. So that means in order to minimize the total travel time, Susie must enter the highway at about 2.19 miles from point A, and her total travel time will be about 0.73 hours. Remember, her speed was given in miles per hour. Okay, 0.73 hours is just a smidge less than 44 minutes. Excuse me. Question number 3. A quart is 57.75 cubic inches. Now, there once was a time when a quart of oil came in a can. If we use 60 cubic inches of the volume of the can to hold a quart of oil, that's to give us a little, wiggle room in the can. Find the radius and height of the can that uses the least amount of material to make. It says round your final answer to place it to the right of the decimal point. You will need the following facts. The volume of a can of radius r and height h is volume is equal to pi r squared h. Notice it's two variables. And the surface area of a can of radius r and height h is s is equal to 2 pi r squared plus 2 pi rh. The 2 pi r squared, that's the top and the bottom. The 2 pi rh, that's that curved side of the can. It's actually called the lateral side. The reason we care about using the least amount of material is that's the cheapest can to make. Okay, the least amount of material is the cheapest can to make. So this comes down to trying to find the cheapest can. Now, in this problem, the assumption is that it takes the cost of the top and the cost of the side are the same. In general, that's not always true. So our solution. Now, our goal is to get the volume because we're trying to minimize volume. Let's see, are we trying to? No, we're trying to minimize surface area. So we want to somehow get a function of one variable that we can give to the calculator. So we want to minimize S. Okay, that's the amount of material to make the can, the surface area. So we need it to be a function of just one variable. So that means we got to take the volume formula, because we know the volume, 60 cubic inches. We're going to take this volume formula with V equals 60 and solve it for either H or R. I think it's easy to solve for H. So we can do that by using the volume formula. And remember, we're going to use volume as 60. It says so right there, 60. And replace V with 60 and solve for H. Again, it's easier to solve for H than for R, because to solve for R, I've got to do a square root, and I don't want to do that. So I'm going to have 60 equals pi r squared H, right, replacing the volume with 60. To figure out what H is, divide by pi r squared. So 60 over pi r squared is H. That's coming from the volume formula, with volume being 60. In the surface area formula, I'm going to replace H, which is right there. I'm going to replace H with 60 over pi r squared. That's all we're going to do. So I can get the surface area to be a function of H. So H is going to be the X, and the surface area is going to be the Y. So we substitute this value of H into the formula for the surface area. So remember, H is 60 over pi r squared. So replace that H right there with 60 over pi r squared. So I'm going to have surface area as a function of H is 2 pi r squared plus 2 pi r times 60 over pi r squared. We can do a little arithmetic with that. We can do 2 times 60 is 120 and have 120 pi. And this r over this r squared, that one goes away, and I'm left with 1 r downstairs. So simplifying, I got 2 pi r squared plus 120 over r. Now let's say you didn't simplify it and you just gave this directly to the calculator. That's fine. The calculator doesn't care if you simplify it or not. So if you're saying, I can't simplify that and it's just too much algebra, I'm going to hurt myself, just key that in exactly as it looks into your calculator and you'll be fine. So I'm going to give this as y1 with, again, r being replaced with x. So let's see here. Okay, make this brighter, quit that, go to y equal, clear it out. Okay, so I'm looking at 2 pi r squared. So 2 second pi, can you remember, r is going to be x. X squared plus 120 divided by x. Now again, if you couldn't do the simplification, just key this in like it looks. 2 pi r squared plus 2 pi r, and then put in parentheses 60 over pi r squared. And again, you would need to keep that denominator in parentheses, right? Because it is an operation. And then quit. Quit. Okay? So we're going to use calc and minimum. Left bound is going to be 0, since we have to have positive results. And for the right bound, I arbitrarily chose 10. Okay? Because remember, that's the radius. I mean, think about it. A radius of a can of oil, that's a radius of 10. That's huge. Okay, so I'm probably way bigger than I need to be. So let me go ahead and do that. So second calc, wanting to do minimum. So choice 3. Okay, now remember, the reason it's doing this is because of my Windows settings. Okay. So y1 is, make sure I have it right this time, 2 pi r squared plus 120 over r. Left bound, I'm picking 0. Come on, enter. It's just not cooperating with me today. Right bound, I said I was going to use 10. It's probably way bigger than I need. Enter. Notice I don't see the graph at all. Okay, I don't see the graph at all. So this is going to be kind of interesting to see, does it find the minimum value? And then a guess of 10, yeah, sure. Notice it found it even though I don't see a graph here. So the minimum h is going to be the 2.12, and that's the minimum volume. It's not minimum volume. The minimum surface area, 84.842875, and so on. Okay, again, my mouse is just jerking badly. So again, I went back to the standard window here. So 2.12, etc., etc. So this gives us the value for r since x is the radius. Okay, so to find h, we use what we found earlier. Remember, h is 60 over pi r squared. We got that from the volume formula. So we're going to use the calculator to find h since it has stored x in its memory location. So this is the way we're going to do it. Okay, remember, the radius is in x. So if I quit this, second, quit. Okay, so remember, h is supposed to be 60 over pi r squared. So we're going to calculate 60 divided by, I've got it too many times now. Back up, delete that one. Okay, open a parenthesis. Okay, pi, and remember, x squared, close, press enter. Okay, 4.2431, etc. Remember, that's the height of the can. So again, 60 over pi x squared. So this means to minimize the cost of a can, or to minimize the surface area, the radius must be about 2.12 inches, and the height must be about 4.24 inches. Okay, the end of section 2.6. That's the end of chapter 2. And remember, that's also the end of the material for test 2. Test 2 is over chapter 2. Again, my mouse is just jerking so badly.